So all these things that we've been doing are very, very mathematical, and for some of you this will be perfect and you're going to hate this. But for some of you, you actually need to see the stuff, and all these equations are confusing you. Well, thankfully, we have a way of representing this graphically, so it's very, very, very easy for you to follow what we're doing, okay? And for this, we use two types of graph. One graph is called a distance or displacement time graph. So displacement time. This basically tells us how far we've gone each second. And then we have speed time graph or velocity time graphs. Pretty much the same thing. Just remember that velocity can be negative, speed cannot be negative, okay? And we're going to do a couple of examples, and you'll see that, you know, there's really nothing to this. So let's see. Okay. So what we're going to do now is just try to represent the distance that somebody moves with the time that they move. And what I want you to do is just, every time that I ask you a question in the video, just answer it in your head and see if you're following what I mean, okay? So in this case, I have this guy. So here's my guy that starts still at 0. So its initial displacement is 0, and starts moving to the right. So if he starts moving to the right, then speed is always positive, but velocity is also positive, okay? So we ask ourselves about the distance at different seconds. So we do what we always do with graphs, right? So it's like 1 second, and then that's 2 seconds, and then that's 3 seconds. And basically what we do is we just take pictures of the guy every second and see how far he's gone. Okay, so at 0 seconds, we agreed that his displacement is 0, so of course he's going to be here. Let's just make a little cross. That's where the guy is at the beginning. And now we need to make divisions for, so I'm going to make 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. So now I ask myself, okay, well, after 1 second, how far did this guy go? Well, if he's doing 2 meters per second, then after 1 second, he's gone 2 meters. So if this is, so let's just write the label. So that's 1, 2, 3, 4, 5, 6, 7, 8. Okay, so after 1 second, he went 2 meters. So I need to go up here, up here. Okay, so let's make a little cross. Now after 2 seconds, he went 2 meters more, so that's 4. So again, 2 seconds, 4 meters over here. Alright. So this starts to look vaguely familiar. Then after 3 seconds, he goes 6, so there it is. 4, that's 8. And it's pretty easy to see that this is a straight line that goes up. And of course it's a straight line, because the speed tells us how distance increases with time. And in this case, every second, the distance increases by the same thing. So each step of 1 second will see exactly the same increase. So we can already make a little line here. And we can see that when the speed is always the same, well, that's supposed to be a straight line. When the speed is always the same, then the graph of our movement, the distance time graph of our movement, looks like a straight line. So that was easy. Now let's do this same thing with velocity time graph. Okay, so let's do that. Let me zoom out so we can still see this. And now this should actually be easier. So I'm going to make a, whoa, how did that happen? Okay. Well, I have no idea why this works like this, but it seems to work like this. There you go. Alright, so here's my axis again. Maybe I should move this a little bit. Yeah, to the right. Okay. And I'm going to do the same thing. So this is the time, and in this case, this is the velocity. So 1, 2, 3, 4, 5, 6 seconds. So 1 second, 2 seconds, 3 seconds, 4 seconds, 5 seconds, and so on. And here we have 1 meter per second, 2 meters per second, 3 meters per second, and so on. So this is in meters per second. Okay, so now let's draw this. Well, this guy is still going at 2 meters per second, right? So what's his speed at the beginning? Well, 2 meters per second, because that's his speed. Okay, so little cross here. And after 1 second, well, it's still the same, because it's always the same. Okay, so 2. And after 2 seconds, well, again, same thing. Okay, and it's very easy to see that this is basically a straight flat line, because the speed is always the same. The guy is moving at a constant speed. So that's how a speed time graph of a guy moving at a constant speed, and this is very important, looks like. And now we can be like, well, okay, so that's interesting. Do you guys remember that I told you that the distance or the displacement was the velocity times the time? Okay, so here, this is the velocity. So the velocity here is this side of a square, right? And after 3 seconds, he's gone 2 meters per second times 3 seconds, right? Which is the base of this square. So if I want to know the displacement after 3 seconds, basically I multiply this times this, which is height times width, or times the base, which is the area underneath this thing, right? Well, isn't that interesting? So if I can draw my movement in a speed time graph, I can calculate displacement just by looking at the area of the little square underneath. Careful, not the area in centimeters, the area measured in the units that are here. So if this says 3, this says 2, then 2 times 3, that's 6. And this, even though it's pretty silly for this example, is going to come in very, very handy when people start moving at speeds that increase with time. So now things start to get interesting. Now I'm not moving at a constant speed, but I'm accelerating. So I start still, and then after a second I'm moving at 2 meters per second, then at 4, and then at 6, and so on. So I'm moving faster and faster and faster and faster. Now, it's actually really, really hard to calculate how much I moved, because my speed is changing all the time. So I'm going to wait until I draw the distance time graph. But I am going to draw first the speed time graph, and then later from this I'm going to calculate the distance time graph. Okay, so let's see. Well, the first point is easy to draw. At the first second, time 0, speed is 0. So here's my first point. Then after 1 second, I'm already moving at 2 meters per second. So let's just say this is 2, 4, 6, 8. So I'm moving at 2 meters per second. And after the next second, the second second, I'm moving at 4. And after the next one, I'm moving at 6, of course. And as you can see, this is a straight line. So that's interesting, right? When I'm moving at a constant acceleration, then the movement looks like a straight line, but not in the distance time graph, but in the speed times graph. Remember, this is not the same. This is speed time, the other one is distance time. And remember how I told you that if I want to know the displacement, I can use the area under this thing. So the area under here is going to tell me the displacement, for example, in the first 2 seconds. And in the first 3, the area under this thing. In the first 4, the area under this thing. Well, do you know how to calculate the area of a triangle? Well, if you don't know how to calculate the area of a triangle, I'm going to show you, but it's actually very simple. So here's a square, and here's a triangle, which takes exactly half the area, right? So if the area of the square is a times b, then the area of the triangle is a times b, and then half, so over 2. So I'm going to use this property to show you how a distance time graph looks. First, I'm going to have to shrink this a little bit. Okay. So I'm going to do the same. A couple of lines. So line number 1, which I'm going to move over. Then line number 2. And then this is my time. This is my distance now. Okay. Well, and now I need my, so 1, 2, 3, 4, 5 seconds, 6, 7, 8, 9, 10 seconds. I'm not going to draw that far, but anyway. And then let's make this a little small, because we're going to need this 2, 3, 4, 5, 1, 2, 3, 4, 5, 10. Okay, and that's of course in meters. Okay, so now, well, at the beginning I'm still, right? And because I'm still, I haven't moved at all, I'm here. So my displacement is also 0. Good. So the first one's easy. Now, how much have I moved in the first second? Well, in the first second, I've moved the area under this, right? So the base is 1, the height is 2, so using this formula here, so the area is going to be 1 times 2 over 2, so my displacement is going to be 1 times 2 over 2, that's equal to 1 meter. Okay, so after 1 second I move 1 meter, that's not much. Okay, there I am. Okay, how much did I move after 2 seconds? Well, again, now the base is 2, but the height is 4, right? So it's 2 times 4, okay? So d equals 2 times 4 over 2, that's 4 meters. Okay, well, that's quite a bit. So over here. How did I move now after 3? Well, after 3, again, that's 3, but that's 6. Now, do you see how this gets bigger and bigger and bigger? So that's 3 times 6 over 2, that's 9. Right? Wow. So now this one goes here. And you can see that this does that. The displacement gets bigger and bigger and bigger and bigger. The distance that I move gets bigger and bigger and bigger. Why? Well, because I'm going faster and faster and faster. So of course, each second I'm going faster until if I'm here, I'm going really, really fast. So in 1 second, I'm going to move a lot. Way more than here where I was going very, very slow. So an accelerated movement looks like a line in here in the speed times graph, but actually it looks like a curve that has a lot of slope in the distance time graph. And the beauty of it all is that I can actually use the speed time graph to calculate the distance after each amount of time. And all I need to do is just, well, draw myself the graph, and then I find the area under this little chunk of graph, use the triangle formula, and there you go, I have it. Aren't graphs neat? And there's something else. Imagine that I have this distance time graph. Well, what's my speed? Well, here my distance is always the same, right? So if my distance is always the same, then I'm not moving at all. So my speed is 0. And funnily enough, you can see that the slope of this line is 0, right? No matter how much I move forward here, this never advances anything. And remember that the slope is just rise over run. So the slope of this graph, the gradient, is 0. And so is my speed. Now when my speed is really high, I will get something like this, right? So that's my distance, that's my time. And then as time goes by, I will go further and further and further. If my speed is really high, then things will go like this, right? If my speed is really low, then things will go like this. If my speed is 0, then things will go like this. So you can see that the higher the speed, the bigger the slope. The speed is the gradient of the distance time graph. Now, if you don't know what gradient is because you haven't done this in math, don't worry. All you need to know is that this thing gets steeper and steeper and steeper as the speed gets higher. So a very steep line corresponds to a very high speed thing that's moving. And a line that's flat corresponds to no speed at all. And a line that goes like this, of course, corresponds to negative speed, right? Because this thing is moving backwards. Now, this can also be used for acceleration. So let's make another graph, and then instead of a speed time graph, I'm going to make a velocity time graph. So here's my velocity time graph, and I have this thing that's like this. Okay, so my speed is always the same. So how much is my acceleration? Well, 0, because my speed is not increasing, and the acceleration tells me how much my speed is increasing. How much is my speed increasing? Well, nothing. So my acceleration is 0. However, if I have something like this, then my speed is obviously increasing. And if I have something like this, my speed is increasing even more. So what this tells me is that the higher the slope of the line in the speed time graph or in the velocity time graph, the higher the acceleration. And if the slope is 0, then the acceleration is 0. So for example, let's just do a quick question. Let's see if you guys can figure this out. In your head, tell me, so this is speed, this is time. I have 3 lines. Line number 1, line number 2, and line number 3. So tell me, which of these lines has the highest acceleration? The blue, the red, or the white? And tell me, which of these lines has no acceleration? Blue, red, or white? Hopefully, you stopped the video and said, well, this one has the highest acceleration because speed is increasing the fastest, and this one has no acceleration because speed is always the same. Alright, so that's it for today. I know it was a lot, especially the concept of acceleration can be a little bit hard to grasp, but it's very important that you practice this a little bit before you go to class. So please do the short quiz after this video to make sure that you understood everything that you had to understand. If you don't, you can watch the video again. You can ask questions, use the forum in the Moodle, whatever you need to do to understand this before you go to class. If you still can't understand, then I will of course help you during class. Good luck.